My name is Kiralee Rule, and I am the Honorary National Secretary of the Australian Institute of Physics. And I'd like to thank you all for joining us today at our next AIP monthly webinar series, focusing on the ARC Centres of Excellence. So welcome and thank you. Before I introduce our speaker for today, I'd like to first acknowledge the traditional custodians of the land on which we work and live. Many of you are joining us from locations across the country and even in New Zealand today. But for me today, I'm located in Lucas Heights, which is about 30k south of Sydney. So I'd like to pay my respects to the Dharawal people and recognise their continuing connection to land, water and the community. I pay my respect to elders past, present and emerging. So today we'll be hearing from the ARC Centre of Excellence for Transformative Meta-Optical Systems, or TMOS. And today we're being joined by Dragomir Neshev from the ANU in Canberra. So Dragomir is a professor working in photonics, thin films and optical engineering, and is the director of TMOS. And today Dragomir will tell us a little bit more about nanomaterials which are being developed by the Centre for new smart miniaturized optical technologies. And for those of you who don't know Dragomir so well, from what I read on the internet, Dragomir is also a bit of a Pokemon fan and has a beautiful dog named Evolution, or Eevee for short. So thanks, Dragomir. I'll hand it over to you.
Thank you, Kiralee. So welcome, everyone. Welcome to this talk. So what I want to tell you today is to introduce you to our Center of Excellence, which has officially started at the beginning of this year. Tell you who we are and what we do and what our program is. And the title of the talk is A New Lens and How Using Nanomaterials We Can Transform Optical Systems. And for those who don't know me, I'm a professor in physics at Australian National University and the director of TMOS. So just with a little bit of introduction to those who are not familiar with the Center of Excellence, though maybe probably all of you are familiar with that, Center of Excellence are the elite high-quality research programs of the Australian government to support outstanding research and develop Australia's international standing in research areas of national priorities. What I will try to convey to you is why is this center, why is TMOS really part of these national priorities? But before we start, so in 2019, the Australian Research Council awarded two centers of excellence in the physics disciplines. And by conservation of brightness, the two centers were dark matter and light matters. So TMOS being focused on the application of light, and in particular for designing of smart and miniaturized optical technologies, making an impact on to the society on the magnitude what we've seen from the transistor and the Wi-Fi, as Wi-Fi being a particular invention from Australia. The Australian Research Council has awarded us $35 million. It started beginning of this year. We have 5 universities: ANU, University of Melbourne, UTS, University of Western Australia, and RMIT. So before I dig into the research and why meta-optical systems are important, why they're important for Australia, I want to introduce you first to the team, the TMOS at TMOS. So we are 15 chief investigators at the 5 universities, as I mentioned before, with myself as the director and Professor Ken Crozier from the University of Melbourne as a deputy director of the center. We are split in multiple disciplines, covering from material science to optics and electronics. But very importantly, now that the center is started, we are supported by an excellent professional team with Dr. Mary Gray as the Chief of Operations of the center, Galina Shadrigova as Business Coordinator, Peter Novotny as Inclusion, Diversity, Equity and Access Coordinator. And to my knowledge, this is for the first time a Center of Excellence has a coordinator in this area to really put focus on how we deal with this big issue of diversity in the STEM disciplines. And of course, last but not least, Samara Thorne is our engagement manager, who is coordinating all the engagement with external stakeholders like industry, government, and schools. And she's the one, if you follow our Twitter account, she's the one who is also posting a lot of the information there. We also built into quite a large international network from 3 continents, mostly from the United States, starting from University of Central Florida, Duke University, CUNY, and in New York, University of Arizona, Northwestern University, and 2 partner investigators at Caltech, also in Singapore, and in Europe, if you can call British part of the community still part of Europe. So back to our original question, why do we need optical systems? So I'll show you here an image of part of Canberra with the balloon, so over the lake. So while we're enjoying this image, what we can appreciate also is how many optical systems are being used to appreciate this image in order for us to observe and appreciate the world. And you might say probably 1 or 2, but the answer is probably a lot more, starting from the photographer who has taken the photograph with a large camera lens and a camera detector. And I don't know how many people have joined today, but I believe tens of screens and cameras also looking at this for us to all appreciate such an image. So the bottom line out of this is that we use so many optical systems every day, and we don't even realize and we don't really appreciate the complexity of these systems. But if we look back into the history, like the challenges, what we have covered across from the Middle Ages, this is probably the first optical instrument that has been recorded in the humankind. So 700 BCE, the so-called Nimrod lens, now in the British Museum, it's been used by the ancient Assyrians to make little models and to drawings and to magnify. It's about 3 times magnification what this lens gives. So if you think, so now fast forward 3,000 years to the current times, what we have is, let's say, a new phone, like this one here, iPhone. You get about a handful of lenses, and the number of lenses that you can get in a phone is totally limited. And this is the lenses, the optical system is the one that is limited the thickness of this phone. So really for 3,000 years, from 1 to about a handful of lenses. In contrast, if you think how many transistors this phone packs in, it's probably more than 1 billion transistors in just for 60 years of development of electronics. So this is a question, are we in optics lagging behind that for 300 years we could only scale up an order of magnitude the number of optical systems that we use? And this is potentially a problem. And if you look at some other examples, like this drone that we have here, the drone carries an environmental monitoring camera in the infrared. And this camera, it has the weight as far as the weight of this camera is the same as the drone itself. So this drone does not fly very far. So this is clearly a bottleneck here, that the optical systems limit a lot of this new application that we are seeing of miniaturized personal devices and monitoring. And this is not just for these 2 examples, but it actually comes across a wide range of developments, and starting from holographic displays that everybody wants to have in their augmented reality set, LiDAR technologies, wearable sensors, and ultra-fast Wi-Fi with the speed of light, so-called Li-Fi. And these are new technologies that are being developing, are forming a whole new revolution, the so-called 4th industrial revolution, which is transforming our society. And this revolution effectively merges the digital and biological worlds, and that merges, or this interface between the 2 worlds is done with using light to interface the humans and machines. And this interface that we see here is very important for this development of advanced manufacturing for autonomous vehicles and medical sensors. However, it's really not something that can be easily addressed with the current optical system, with the current and bulky lenses that we use. So what is clearly on the agenda is that a new concept is required that optical systems need to rely on in order to meet the demands of this new Industry 4.0. And this is where our area comes in. So this is what Metaoptics is. Meta coming from the Greek word meta, meaning beyond, so beyond the existing optical systems. And in Metaoptics, for the first time, we have manipulation of light, not in the conventional sense of refraction and reflection, but by scattering from small nanostructures, nanoparticles that are arranged in arrays, as you see here in this image, arrays of nanoparticles that capture the light, kind of concentrated inside as a resonator. If you think about it, like you can think of these things for light, like a drum for sound. So this is one of my drums here. So what you heard of this drum is the resonances that this drum has, but also the different sounds that this drum can give. In a very similar fashion, the small nanostructure resonators for the light and allow for the light to escape after it's captured with specified and tailored polarization, color, and phase. And what this new concept allows us is to make lenses a lot thinner, so 1,000 times thinner than a human hair, but at the same time to make a complexity of the optical system and the functionality a lot bigger. For the first time, one can just make a lens, not that can just image cells, but can also be a smart lens that can distinguish between healthy and diseased cells. Furthermore, the fact that these nanostructures are fabricated on a planar film allows sort of to merge the chip making, like we know from the electronics industry, with the optics making. So the optics fabrication is becoming the same way as electronics making. And what this would allow is to make such big lenses that we usually know, and they're very complex to manufacture, big lenses for astronomy and for space science that requires complex polishing, three-dimensional polishing technologies to prepare such lenses on a flat surface in the same way as making chips. And you can do this all across the entire spectrum of light, starting from visible to the infrared. So this is a very powerful technique, and this is what this new concept gives us. If you look at the literature of meta-optics or meta-surfaces as a more broader concept, you will find lots of different meta-surfaces composed of different nanostructures of different shapes, as you can see here in these several images, different shapes, materials, different materials coming from plasmonic and metallic structures to the electric high index structures, to be able to make very complex functions that interleave in a single surface due to this discrete arrangement of nanostructures. In addition, because of this complexity, one now is able to perform very complex, arbitrarily complex operations in the optics on the optics field, such as image processing and image classification and image recognition even. And furthermore, because these elements are nanoscale elements, they can be potentially reconfigured because of their nanoscale volume. And so these are very powerful concepts, but you might ask, what is actually the common physics or the common science that goes behind all these different types of elements? And the truth is that the science actually behind this resonance scattering is described already more than 100 years ago, and it's been known to humankind with this man here, Gustav Mie, who already in 1908 described the scattering from small particles. The scattering was given by this formula, given two types of coefficients, which are given here. Effectively, these are the electric and magnetic modes of the scattering. So this was the new thing that he discovered. So we have two types of modes that exist simultaneously in the scattering, two types of resonant modes, one which are due to the oscillations of the electric fields. These are the electric family of the modes, and another magnetic family, which are effectively oscillations of the magnetic field in these particles. And these modes have different nodes and complexity, like from the fundamental to the higher order mode. So while this could be a bit abstract, maybe we can illustrate this again with my favorite example of a drum. And what you see,
here's the lowest frequency vibrational pattern in a circular membrane. This circular membrane is a piece of dentist rubber dam. It's stretched over a short length of PVC pipe and held in place with some rubber bands. And this lowest pattern, the entire membrane moves up and down together as one piece. The whole thing moves together.
With the similarity of
here's the second pattern for the same membrane, occurs at a little bit higher frequency. Half of the membrane moves up while the other half is moving down, and there's a line right across the diameter called a node that doesn't vibrate at all.
So then we will change the frequency to a higher value. So you can see this movie also on the YouTube.
Here's the third pattern.
So you get the third
membrane. There are two sections. Actually, it's kind of like a cloverleaf pattern. Two opposite sides of the membrane move up together, and the adjacent sections move down. So
I'll stop this one so I don't go too much over time. So I hope this example of the acoustic resonators clearly illustrates actually what's happening with light when they enter these nanostructures, and what are they how these nanostructures are excited by different modes. What is important to mention that each of these modes, at least for spherical particle, is resonant at a particular wavelength. So the wavelength of the resonance for this mode is different. And what is important also to point out, the difference between optics and sound is these two types of modes that we have in optics, electric and magnetic modes. So what I have shown you here on the right of this slide is the resonances or the transmission of light through modes, through array of such resonators. However, this time for simplicity, I have not used spheres, but I have used cylinders. And what you can see here is what happens in the transmission. So at each of the resonant frequency, the light is being captured inside these resonators and is being scattered backwards. So that's why in the transmission of the light, we're seeing these dips. So minimum in transmission, and if you look in the reflection, you will see a maximum in the reflection. What is also important to point out that at each of the resonance, it's a resonant phenomena, at each of the resonance, we have a pi phase shift of the transmitted light, change of the phase of the light with pi. And this is what allows this phase manipulation. However, at the early stages of the field, that was hindered by the fact that with the right phase accumulation that you get, you also get this huge modulation of the transmission, the transmission amplitude and transmission intensity. So the big change in the field came also as part of our research when we realized that by changing actually the geometrical parameters of these disks, not just to mimic a sphere, but changing the size of the disk, keeping the height the same, we can bring together the two modes to be oscillating at the same frequency. So one is electric, one is magnetic mode. And so in this way, we can bring also this phase modulation, which comes closer and closer together. So if I continue to change the size, we can perfectly overlap the two modes. At that time, so this was in this paper here published in 2015 from our group at the ANU, what we were quite surprised to see that at the position where we actually overlap the two modes, the electric and magnetic modes, by changing the diameter of this disk, we actually saw a reduced transmission. So we were quite puzzled because we thought this reduced transmission is due to the reduced scattering. However, if you look at the phase profile, it was clear that the phase is now changing not just by pi, but by 2 pi phase shift, which was an indication of a very strong resonant phenomenon. And if we change the disk at the exactly particular size for its height, then what we could see is that the entire transmission of the light became flat. So we had no resonant phenomena inscribed in the transmission, and all of this scattering was entirely into the phase accumulation of the light that is transmitted through an array of such disks. And this particular condition is called the Huygens condition, and it is called Huygens condition because it mimics how Huygens principle works, and the Huygens sources that only scatter in forward direction. And this is exactly a case where we have this only forward scattering for a particular diameter of the disks. So now what one can do is, using such this particular condition that we have entirely unitary transmission through an array of such disks, what one can do is to line up disks of different sizes in order to modify the phase of the transmitted light. So the different sizes effectively shift slightly the resonant frequency, and then the light that comes from this part of the metasurface, so keep in mind this is all nanoscale dimensions, is only the light gets only modulated by the phase shown here. The second one has a phase accumulation shown in this curve, and so on and so on. So effectively, this structure poses a phase gradient, linear phase gradient on the transmitted light, and this happened with unitary efficiency for the transmission. So this was a groundbreaking result because it allowed the community to make optical elements that have very high efficiency in transmission with full phase coverage from 0 to 2 pi. So you name what phase you want, you can dial it in on your metasurface. So effectively, any phase profile can be encoded on a single surface. Just as an example, as I showed you before, a typical example of a meta lens, a simple metasurface that focuses light in a single point and can be used for imaging as well. So the way that works is, for a lens, one needs to have a parabolic phase inscribed on the beam that is transmitted through the meta lens. So this parabolic phase, now we can discretize in particular grid. It could be square, it could be hexagonal, doesn't really matter. And then for each of these phases on the discretization, one can assign a cylinder with exactly particular size, such that such elements of multiple disks of different sizes will inscribe a parabolic phase onto the transmitted beam. If you want the lens to be bigger, you just need to fold in 2 pi this transmission of for the light and encode more and more in this 0 to 2 pi transmission. So this is what allows you to make a lens. If you want to make a beam steering device, you can just plot a linear gradient and so on and so on. So this was the basic of the meta-optics, and the field really exploded after the ability to create highly efficient devices made of nanostructures. But let's just go back a little bit into the history and see how this field had developed in Australia. So the field in meta-optics in Australia, when did it first start? So everything has a long history from the meteorite, but if you look in Australia and dig a little bit in the literature, you will find this work published in Nature in 1977, just a few months before the release of the first Star Wars movie. So can you guess who were the authors of these papers. I hope some of them are here. So these were two blokes from the University of Sydney, David McKinsey and Ross McFadden, who first described how to model a cubic lattice of particles and the permittivity and conductivity of such lattices of small particles. Later on, both of these guys, together with collaborators, so with Professor Ross McFadden, further described the problem of cylinders that I also showed you before. So this was 1979, and not far later, a very bright scientist, Professor Anne Roberts, now professor in Melbourne, working at the time with Ross McFadden, and also described how to make special devices like bandpass filters made out of small nanoparticles. In this particular case, annular apertures in a gold film. So a long history in Australia, and in 2011, again, Ross McFadden, together with colleagues at the University of Sydney and the ANU, were the first actually to coin the term Metaoptics for the whole world, done in this paper here. So that's why lots of people have asked me, what is Metaoptics? Why do you have such a technical title in your center? And the reason is that with keeping the Metaoptics in the title of our center, we keep the legacy that this field has in Australia. And since 2011, the field has been really active and very, very diverse, with a number of works done by the TMOS team, but also by other researchers, including nanolasers, holograms, tunable beam steering, single photon sources made out of such elements, tomography for quantum states, and very high efficiency detectors. And that's what the foundations that our center builds on. And at the time, while this was a very vivid film when we put in our application for the center, most of the work that has been done is really on static type meta-optics. So once you fabricate it, you fix it, and that's how you use it. However, in the center, we want to build a lot further beyond this static picture, and to come to an active meta-optics, being able to actively generate, dynamically manipulate, and detect light in these ultra-thin materials by coupling of such nanostructures with semiconductors and with other materials. And you can think this might be an easy task. However, if you think about the fact that the light is a particle that doesn't really easily interact with matter, it's actually very difficult to do such things in ultra-thin materials, such as few hundred nanometers thin materials. So this is where the challenge is, and this is where this resonant phenomena of the light build the foundations for these light matter interactions at the nanoscale for light generation, dynamic manipulation, and detection. So in our center, these three parts build the pillars of the research program. And in the next few slides, I hope to show you a little bit of the flavor what we do currently in this research program. So we have three pillars with several programs under each pillars and several capabilities enabling this research in the three pillars. However, the real impact of the center is by combination of the three pillars to really target applications in holographic displays, night vision technologies, wearable optical sensors, LiDAR type technologies, remote sensing, and ultra-fast light-based Wi-Fi technologies. So starting with the first team that we have, research team on light generation, which is aimed to control wavefronts, but by ultra-thin materials, control the coherence and quantum properties of the generation of the light that is emitted from ultra-thin materials. And as a particular focus is to be able to generate color holograms with and light states with tailored quantum properties. So I want to run you through a few examples. In these examples, I won't go into details deeper into the physics, but I hope you can contact me later on, or the the researchers behind each of these research areas. So when we talk about nanolasers and nanolasers array is what you need in order to make your phone to generate your holograms. If you are Star Trek or Star Wars fan, yeah, you need a device that can emit with a controlled wavefront in order to generate a hologram. And you cannot do this with the LED. So with our displays that we currently have in the phones, you need a coherent light. If you want to build this in this display in an augmented reality set or in a mobile phone, you need this to be highly miniaturized, sub-micron level. And this is the research done by the guys, led by the guys at the ANU, Jagdish and Hotan. They developed in 2013 the nanowire lasers, which, however, were broken down to put on a substrate, and they were emitting in the plane of the substrate. So if you want to do a display, however, all these lasers need to emit vertically. You need to emit into to reconstruct the wavefront. So this is what the research at TMOS is going on. So last year, the team at the ANU worked on putting such lasers, such nanowire lasers, into a bullseye apertures in order to make a highly directional emission, as you see here, and also currently developing new types of lasers like these micro ring lasers that can emit broad or multi-mode type emission. However, this work has lots of new challenges to explore. In particular, once you put these arrays, these lasers into arrays, how to control their coupling, how to control their wavefront, how to make this electrically driven, and how really to build this in a device. So these are areas which are open and that our center will work towards this direction. Once you have lasers that generate a particular wavelength of light, if you want to change this light, you need to do something different. So what we've been doing at the ANU is using so-called nonlinear processes, which do interactions between several laser beam in nonlinear materials to convert the light from one frequency to another frequency. And as a particular application for this process shown here, which is called some frequency generation, where two photons combine to generate a new photon at a higher wavelength, we have shown how to use this process, how to enhance this process in metasurfaces using this resonant enhancement of the light fields inside the nanostructures, and use this for upconversion of infrared images using a pump beam to convert these images coherently to the visible domain, such that can be observed either by eye or by standard CMOS cameras, such that these type of night vision devices are not affected by the thermal noise or by other difficulties with infrared detection. So to do this, a bright colleague of mine who is now in UK, Mohsen Rahmani, developed this kind of technique to actually collect very high nonlinear nanocrystals from aluminum gallium arsenide fabricated here by the group of Professor Jagdish and Hotan, to peel them off into a polymer layer and to be able to put them on a transparent substrate such that they can really be used as metal surfaces to enhance the light matter interactions. And as a recent example, which is on this archive publication here, we were able to show that an infrared image, so this is taken by a conventional infrared camera, can be converted to visible direct to the green light, so and observed on a very cheap CMOS camera, $200 camera from bought from Tollabs. So we proved this convention, this concept of image conversion with the images are correctly, the images of these Siemens stars are correctly displayed. Well, there's still a lot of work to be done to be able to enhance this conversion efficiency so that these devices are really to be able to really enhance the performance of these devices to be comparable with the infrared imaging sensors. And of course, bringing this to the eye level kind of eye form or spectacles form type type devices with large field of view and good directionality of the emission. And my colleague Ken Crozier at University of Melbourne has already proposed and will be working on such schemes using upconverting nanoparticles coupled to such metasurfaces. The TMOS also, our center also has a large focus on quantum, enabling quantum technologies, quantum materials, and single photon sources. In particular, the group of at UTS, Milos Todt and Igor Aharonovich, have been working for many years now on single photon sources in two-dimensional materials such as hexagonal boron nitride. And you see here all these colored dots are single photon sources that are really single and really quantum emission, because this second order correlation drops below 0.5, so really giving a quantum light. However, a lot of these emitters, as you can see, are difficult to distinguish. And within the TMOS framework, they're exploring the coupling of such emitters to nano antennas to be able to access their internal degree of freedom, like a spin or valley polarization of such emitters, in order to enhance and to really design their properties. The group is also exploring other materials like an enhancement of other materials through nanocavities and microcavities such as diamond photonics. But of course, there are lots of open questions still that we need to resolve under the TMOS framework, including what is the nature of these defects, how one can control these defects and deterministically induce such defects, giving indistinguishabilities of such emitters, and being able to properly tune such materials. The work led by my colleague here, Andrei Sukurukov, extends this further to not just to single photons, but to multi-photons generations through spontaneous parametric down conversion for entangled photon generation, and really measurements of these multi-photon states using metamaterials and meta-optics to be able to do a single shot quantum state tomography. Of course, a lot of open questions in front of us for the next years to work on generation of the entangled photons of different spatial modalities, which is something unique to these metasurfaces, and transformation of such multi-photon states from one quantum state to another, and of course, looking at applications in quantum imaging, communications, and spectroscopy. Within the second team for light manipulation, the center aims to develop meta-optics for dynamic light manipulation in space and time, and this will be for high modulation with wide angle and high speed for Li-Fi and LiDAR type technologies. And within this second team, we have several works that are strongly going ahead, in particular using metasurfaces for image processing. This is a direction led by Professor Anne Roberts at the University of Melbourne, who have shown that just a simple layer of metasurfaces can do a spatial filtering in the K-space without needing of complex imaging systems, 2F imaging systems with lenses. So that can be all done in a single layer to produce so-called edge detection of the images. And these are very important filters for autonomous vehicles, where all these edge filters are really what is used in currently with electronics to make these self-autonomous vehicles. In our group, we have also explored these directions by looking at the resonance enhancement of such filtering through mirror resonances. In particular, here, as you see, the edge detection of the Australian Parliament published recently in the ACS Photonics. And Anne has gone a step further together with Tim Davies to really apply such processing to live cell imaging for phase contrast microscopy. And here with the acknowledgements to Tim Davies, who is associate investigator on the center, just one quick video to show how such imaging of live cells can be enhanced by using a nanophotonic devices or metasurfaces of this kind. So the metasurface is in the plane, and on top of the metasurface, which is called here the device, so this is of the device, there are various cells that are being deposited. So you see here, there are lots of cells, but without the device, you cannot really see where the cells are. However, once the device is being moved in the field of view of the camera, you can see huge amount of cells that being deposited. So really this phase contrast microscopy enhances the imaging. It's a really simple opportunity to incorporate in any microscopes in the world. Of course, lots of open questions here as well. Implementing of complex optical filtering, switching, and tunability of filtering functions, bioimaging, and microscopy applications. The group at RMIT, Shiraz Shiram and Madhu Bhaskaran, they have also gone further than this, basically putting multi-layer optics, multi-layer meta-optics, to generate a neuromorphic meta-optic system, which with the fact that these stacks, effectively stacks of metasurfaces, what you see here, can mimic the functions of the brain as a real neural network. So the designs are fabricated by another bright guy at RMIT, Ben Cumming, and use really for image processing and image classifications. And Ben has gone a step further to apply such schemes for adaptive optics, being able to really stabilize a star using such a neural network when you look at the star through the atmosphere, which is normally would require complex and dynamically tunable optics, adaptive optics to control. Again, multiple important questions that are in front of us to be able to dynamically reconfigure this neural network, put nonlinear activation layers really to mimic the work of the brain. And tunability is a big part of the system of the center, because tunability is what is required if you want to reconfigure any optical system. As an example, of a lens that is needs to focus on different object has to be reconfigured to have focal length in order to focus at different depths of the objects. And the group at RMIT have mastered stretchable and optoelectronics with electronics controls inside, and this is a technology that is being translated in the medtech. They're also developing materials, phase change materials that can be used for blocking infrared vision, so really blocking the thermal radiation coming out of this boiling water, as you can see here, like a VO2 materials with boiling water and without VO2 materials with boiling water. You see this red signature of the hot water inside. Well, this is completely shielded if it's covered by the VO2. Going a little bit further, because I don't want to run out of time, so tunable meta-optics, we explore multiple platforms, including liquid crystals, electro-optics, and micro-electromechanical systems at the University of Western Australia. And we work really to develop this in a working type devices. The last theme, the detection part of the center, is the detection of images or an imaging of the invisible properties of light, such as infrared light, phase, and polarization, and so on. And this is very important for application when you want to look into through the smoke. So this is infrared vision in a fire. So a firefighter can see a person lying on the ground here using infrared vision. So Meta-Optics infrared vision could really be helping to save human lives here. And as a start, there are several developments. So Professor Ken Crozier is developing this miniaturized spectrometers that are based on structural colors in silicon. And because of the resonances, each of these parts are resonant at particular wavelengths. So you see a clear image here of the different wavelengths and the colors of different wavelengths that are resonant, and be able to detect immediately with a very high accuracy the spectra of the incoming light. and that will be developed further to apply for hyperspectral imaging and realize miniaturized FTIR spectrometers, and really find the optimal detection responsibility to be able to identify chemicals or other target molecules that are in close proximity with the spectrometer. And the group at the ANU have further developed nanowire type detectors in order to detect light with different polarizations. You can see here the nano hashtag detector published last year in Science. And the group of Francesca Jacopi at UTS have been also exploring a new platform of graphene of silicon carbide in order to make new types of detectors when the graphene is really enclosing the silicon carbide on the top. And again, lots of open questions to develop for high performance angular selectivity, polarization, and quantum level detection. And last but not least, the group at UWA have this very exciting technology, mercury cadmium telluride detection, which is unique in Australia, and just a few of these in the world. So they are clearly the leader in this, creating infrared detectors and mid-infrared detectors. You can see here a working prototype and one image of this working prototype, really in the infrared. And notice here this visibility, what's in the pocket of this person here. You can see through the clothes, really for important applications in monitoring, and combined with security, and combined with MEMS type technology, can be used for hyperspectral imaging, monitoring of fruit and agriculture. But of course, the whole impact of the center comes together when all these three topics are really combined. And this goes into multiple technologies for transport, health, defense, education, communication, and agriculture. Last year, the Australian New Zealand Optical Society released a report for the photonics industry in Australia. So if you haven't read this report, go to the Australian New Zealand Optical Society website, optics.org.au, and you will see that this is a vivid industry, and it's really building a lot and is growing on this new type of technologies, and is forming at the moment $5.4 billion in the Australian New Zealand economy, employing more than 12,000 people and over 500 companies. And we expect this is going to grow in the next years due to this development of Industry 4.0. And special thanks to the authors of this report, John Harvey, Simon Poole, John Lincoln, who really made incredible work here, and are hoping to show the growth of the industry in photonics in Australia in the next years. As an example of the industries in Australia, one of our partners is Seeing Machines, and they're working in driver fatigue monitoring, which is a big, important case for stopping road accidents or fatal road accidents. It's a huge market, but of course comes with huge problems because every car is jam-packed with equipment, and there is no space to put enhanced driver monitoring inside the car. So this is where these miniaturized optical technologies come into place to be able really to illuminate the driver, to do face ID of the driver, so you won't require any start engine key, but also be able to discriminate the reflections from eyewear, such as glasses here, which will allow such technologies to be really accurate in detecting the awareness of the driver on the road, such as to be able to switch between self-driving modes and manual operation of the modes. And there is a huge industry pull to the whole field. I'll just very quickly describe what's happening across the world. So this is a graph of different applications like vision here. There is a TRL level on the bottom. So the ones on the left are higher TRL levels, and the ones on the right are lower technology transfer level. So we're already seeing several companies in the field. So MetaLens is making lenses for mobile phones. Lumotive is working on LiDAR type technologies. iPhones already have part of such technologies for Face ID, and we're using it. So this is how the Metasurfaces look like. It's already in the phone, but we also see huge growth in AR and VR type sets, polarization imaging for defense and so on, and image classification for real identification. Samsung is pushing really hard holographic displays. A company called Metaoptics is doing notch filters for protections of pilots, especially from laser illuminations. And somewhat on the lower tier level, we have the microscopy parts, as we saw from Anne Roberts, but also from other groups, and biosensing based, optical sensing based on Metasurfaces as coming from some of the initiatives also at the ANU. The center has multiple partners. I'm nearly finished, multiple partners that are committed, but of course, we have partners that are really happy, looking forward to engage in the future, looking for opportunities and joint ventures, so to say. And beyond that, beyond the industry, what the center aims is to really drive a multidisciplinary and inclusive culture for leaders by promoting several programs in education. So we've already run several colloquia, 2 colloquia. So today we had a very exciting colloquia by Professor Kishan Dulakia on bioimaging. And we want to support such activities in Australia for everyone, really also to help in the educations in STEM, bringing some of the work forward, helping with the school curriculum and public engagement with everyone. And last but not least, we are really committed to equality, any types. We have focus on gender equality, and we have done already a women-only recruitment. We had 200 women applying for such of the TMOS position under pandemic situation, so it was exceptional. We have hired already the first round of researchers for the center. And we will continue to help these by training programs to reduce biases and improve training. And so last slide to everyone, I welcome you to work together. There is plenty of room at the bottom, as Richard Feynman has said. There's a lot of work to be done, as some of the open questions I showed you, and I hope we can work together in the discovery of new science, but also in transforming this science to the new industry to make impact on the society. So thank you everyone for listening.
Thank you very much, Dragomir. This was a terrific talk. Your centre is doing a lot of excellent work with a lot more to come, I can see. So we have a question and answer down the bottom. There's a little button down the bottom of your screen if you wanted to put some questions in, and I will read some out for Dragomir. So we have a couple of questions already. John Canning has asked a couple of questions. The first one was with respect to your drum video that you were showing, your YouTube drum video. He asked the question, but drums are macro modes from the cavity, not acoustic scattering. Is this right?
So drums are macro mode from the cavity. Yeah, that is right. You can also do scattering, and that also works in a similar fashion. But they are, as I said, they're different in with respect to the optics to many aspects. So it's good to draw this analogy because it's really visual to see how the membrane operates. But I wouldn't stretch it too far, indeed.
Excellent. So we have another question here from Andrew Wee. What is the role of your international collaborators?
So excellent question. So Andrew is a partner investigator on the center, and thank you, Andrew. So we have seen a very difficult time last year because international collaboration to a large extent relies on exchange of people to be able to network, to generate the new ideas, and to place students in the new environment so that they can learn and to give. And that's been all taken out suddenly. So at the current stage, until this previous times return, that we can really exchange students and exchange visits between the collaborators. What we will aim to do is build all of our partner investigators into our colloquium program. So wait for invitation in the next months to speak, and that will be open for the entire Australian community, and we'll be in these hot topics of research. And I hope by the end of this year we will be able also to be more interactive on personal level.
Fingers crossed. Excellent. Thank you. And Andrew, thanks you for that answer. So we have another question from Suvanka Sen, who says, wonderful presentation, Dragomir, thank you. Just out of curiosity, can meta lenses be used in concentrated photovoltaics for renewable energy applications?
Thank you, Suvanka. So it's a very important question, and maybe half of the community will answer yes. I will be a bit more cautious, and I will say that one of the difficulties but one of the drawbacks in the Metaoptics system is the fact that they're highly dispersive. So once you start dealing with very broad spectral bandwidth, that is not an ideal application for Metaoptics. So indeed, I showed you MetaLens is one of the companies that is trying to put this for mobile phones. So this is indeed what they're showing at the moment, operation of the order of 200 nanometers bandwidth. But this is to some extent is okay for mobile phones, and can be done with can be improved with multiple layers of lenses. However, for solar concentrators, I believe that will be a very hard deal, and probably you will be better off still using a mirror type optics.
Thank you. I'm going to ask a question of my own now, if you don't mind. These beautiful photos and pictures that you showed, I guess they were TEM images of the cylinders of different diameters. How are these materials actually made? Are you making them through etching processes, or how are you controlling and making these materials?
Thank you, Kirli. So this is very, very good question. So at the moment, how things are made are done mostly through electron beam lithography. And this is kind of standard what people use in the lab. And it is good, but it's not a high throughput device, high throughput techniques. So UV lithography is something that we are looking. And I just wanted to show this example here, which is a little bit different. This is from Ben Cumming at RMIT, who is using actually 3D laser writing at a very, very small scale. So very super resolution laser writing effectively to do this. So, but again, this is less of a scalable technique. So once this technology needs to go commercial, it needs to be working with foundries, with the CMOS foundries, and needs to comply with all the CMOS regulations. However, it is possible, and that's what we are looking really actively.
Excellent, thank you. Okay, we've got time for one very last question, again from Suvanka. Can we design, in theory, a spectrum-selective metasurface or metasurfaces for manipulation or detection applications?
The short answer is yes, and it's a very big field. Yeah, so this is one of the applications which metasurfaces are really important, and really, I believe, this is my personal opinion, but I believe this is when metamaterials and Metaoptics will make a huge impact, because you can incorporate the lenses with the dispersion, so you can make hyperspectral imaging. For example, you can focus all your different components into different parts of your chip, of your detectors. You can do all sorts of other interesting ideas. So I believe that will be a huge application.
Wonderful. Well, thank you very much, everybody, for joining us, and thank you to Dragomir once more for a really thorough talk about TMOS and the work that's going on there. So thanks again, everybody, and we'll see you next time.
Thank you as well. Have a good weekend, everyone.
Excellent. Thank you.